Important thing of updating that inner product delta, that is something we have to take up. That is the most challenging thing. What we have obtained so far, we obtained that lattice. The structure was like this. If I write EPFN, actually you remember there was a subscript P comma N actually, but then I dropped. Ideally that subscript should be there. It means that you take data up to nth index, based on that do the least square minimization, that is orthogonal projection, find out the error, and that error's last component. But since it is still n only here, I am dropping that n, assuming that we do understand the implication. These two signals, this one and this one, that is more important here. This point is EPB n minus 1, but remember, when I write EPB n minus 1, it means not that there is a vector whose nth component is this and n minus 1th component is this, not at all. This means I took data up to nth index, found out that least square of minimization, they found out optimal combiner coefficients, combined the columns of that matrix involved, and then found out the error. That error vector's last component. Here it is not the last but one component of that vector. That vector itself is different because I am taking data up to n minus 1th index. Then I am doing least square minimization. I get a new defined set of combiner coefficients. By them, if I combine the columns of the data matrix, I get a new defined orthogonal projection. Then take the error, last component of that error vector. Okay, do you understand the difference? It is not that there is one vector whose nth component is this and n minus 1th component is this. So I am dropping the subscript, but if I really put the subscript here, EP comma n, then bracket n, and EP comma n minus 1, then bracket n minus 1, then it clearly indicates that. Just for saving space and all that, I drop the index n, but then you don't get confused. You understand the real meaning of these two, okay? Why not? I give you, this is keeping this in mind. I made one statement, I think in last to last class, that I will make a sequence this way. This is my sequence: E, P, N, B, N. I'm not dropping the subscript for the time being, which I did in the previous page. Then E, P, N minus 1, N minus 1, B. EP n minus 2, n minus 2, B. This is my sequence. These are such a sequence whose n minus 2th element is this, n minus 1th element is this, nth element is this. This is my sequence. Good that you are trying to understand. Please understand that this is the sequence. Where this value was obtained from what? I took data up to n minus 2th index, found out orthogonal projection error vector, last component of that vector. Here I took data up to n minus 1th index, found out orthogonal projection. Those two projections are not same. Here you get a better set of combiner coefficients. Again, find the error, n minus 1th component. That's last element of that. This is my sequence. If this is the sequence, obviously this is the value of that sequence. This is the element of the sequence at the current index. This was at the previous index. So if I take the sequence and then delay it, definitely this will be delayed and you will get this, because this is my sequence, mind you. You understand this? This is my sequence. And obviously, because from here by the computation, now how do I assure? You can still ask me that how do you ensure that that is the sequence generated? Fine, I will by this lattice computation, I will generate here EP plus 1 Bn. and that is based on what? Data up to nth index. So, EP b n minus 1 by taking data up to n minus 1th index, then sorry, let me complete it then. So, you see this guy and look at this guy, this will be used again in the previous next stage, isn't it? But here what I have done, like here data up to nth index was considered, here also data up to nth index, that will be delayed. Okay. That is, if I start with EPB and that is okay, suppose you give me this thing, okay, I use data up to nth index, found out the error vector to the last component. Then by the computation I am generating the same thing just for p plus 1th order, but the same thing. Okay, so if I am delaying it here, by my previous claim I am getting that one step delayed element of that sequence. Here also I will get the same. Important thing is these coefficients. Coefficients are delta Pn by sigma P n minus 1 square, right? B square, isn't it? This one. This is how to remember. EP, I mean, what is forward prediction? Then the previous order forward prediction minus this side. The inner product is common, delta is common, but norm square will be from this guy. From this guy, okay. And here it is okay, these two coefficients dot dot dot, and in the first stage you remember I did the first stage separately, first stage, because I told that suppose when I derived the lattice I told that okay, I will consider at least p equal to 1 and then go for p equal to 2, p equal to 3. But what happens to p equal to 0 and all that, you know, that I did separately. You remember this I did, and then based on that only I defined what is E0 NF, what is E0 NB. This is your xn, like this, okay. So here you get the sequence E1 NF, sorry, you can put this way. Here you get E1 B n minus 1, like that. The 0th stage. Now you see, so lattice recursion is, I am not writing the equation for this separately. EP plus 1 Fn is this minus this times this and so on and so forth. So once you know the parameters at any index, all the coefficients are time dependent. Unlike that lattice, here all the coefficients are time dependent, and at each index n, when you find out the coefficients, then you use them to filter. Xn, this EP, Fn, and these are only signals, these are not parameters. Once you know the multipliers and all, at that index of time, whatever signals you just go on filtering them, you get these various signals. Okay. And how the parameters are treated? Parameters are treated like this at the 0th stage, sigma 0 n f square and sigma 0 n b square, both are same, and that was lambda times plus current 1, isn't it? So using, so at the moment nth index, current index comes and new data has come, you find out this new norm square. delta is a problem, but suppose by some hook or crook we know all the deltas for the timing, suppose. So deltas are suppose known to us at each index, so somehow. Then we only need to know this sigma 0 n square, and this is sigma 0 b, but n minus 1 square. So this is this was obtained in the previous stage and stored. Okay, and the current one we stored for the usage at n plus 1th index, current one for this. Okay, so using that we find out these ones. Then we have how to obtain the sigmas for the subsequent stages. See, it becomes adaptive because data comes in, so data determines the two norm squares, two sigmas here, and from these sigma squares, in general recursively I obtain the sigma squares for the subsequent stages by those recursive equations. Sigma, this we obtain, isn't it? And please correct me if I am making this one be sigma p b n minus 1, na? So mind you, this is how it is adaptive, because data comes, data changes the norm square at this, and then those norm square are used order recursively at the same index to find out the norm square, these variances for the subsequent stages. Using them, the coefficients are changed. Using those values, the corresponding prediction errors are computed. In fact, those prediction errors will be used to update deltas. That we will see. Deltas will be updated. It's not possible to order update delta. The mathematics does not allow actually. It's not possible. So what we will be doing, you know, for every stage we will be time updating delta. That's from the previous value of delta. We need some storage then. We need to store the previous index value of delta. That will be used to time update. That is to get the current delta Pn from delta Pn minus 1. But that will be also using the two errors available to forward the forward prediction and backward prediction errors available. Those also will be used. So how the adaptation will go on, that at the 0 stage, so consider 0 stage, xn comes, so the two variances change. Okay, and deltas will be what? They will be time updated from the previous value plus the two prediction errors. And then by order recursion you go to the next stage, you get the new variances, and there you time update the corresponding delta, but that will be using previous value of delta plus these two prediction errors which are computed at this stage, so on and so forth. So it is adaptive, you understand, but adaptive means exact computation, and as more and more time passes, basically this will become better and better estimate of the actual optimal forward and backward prediction errors, because underlying mechanism is that least square minimization. More and more time passes means more and more data comes, and you know the underlying mathematics, no? That it will be better and better estimation. Okay, but it's purely adaptive, no approximation anywhere. You understood that adaptation phenomenon, isn't it? Because at each index n I am adapting the coefficients. Variances are updated order recursively and using the two prediction errors available with us and the past value of the delta for that particular stage. By some formula we will be calculating current value of delta. Okay. So now our main task remains as to how to compute the current value of, how to time update delta. Let us spend some time on that. So to do that, we set aside the lattice thing. We come to some general real now. I was just discussing yesterday, but there was time was short, so I could not explain properly. So let's go to some definitions. Suppose you have got some vectors u1n dot say uln, L number of vectors. You form a matrix un. There any vector here ukn is of this kind, uk 0th index, uk 1th index dot uk current index, normal. Wn column space. Okay, there is a space spanned by these columns. Space spanned by the columns of this matrix, this column vector. There is a column, I call it loosely column space, and there is Wn. Pn perpendicular, you understand? they are orthogonal projection and projection error operators ops for Wn, this space Wn, fine. Dn is an external vector, okay. Here I want to find out this estimate, this projection. It could be either Pn dn or Pn perpendicular dn, because when you have Pn dn, Pn perpendicular dn is no problem, you subtract from dn. So maybe I write directly. This I want to relate somehow to mind you, the two lengths are different, because when I say P n minus 1 perpendicular means I have got columns like U1 n minus 1, U2 n minus 1, UL n minus 1. The last row of this matrix is absent. Okay. Dn vector also not, the last element is absent, is only Dn minus 1 vector. There I do a projection, and here I get a projection. Of course, its length is 1 higher than here. But even where there the first n minus 1 entries are not same in the do, because these are two projections are different. You get different of combiner coefficients, because here Dn and these columns, they have got one extra data present, isn't it? But I want to somehow relate this with this. You understand, this is a time recursion, n minus 1 to nth, but it's not easy. It's not direct anyway, no way it is direct, it's not easy. To understand this, suppose I consider this situation. And you remember pi n vector? In case you have forgotten, 0, 0, 0, last component is 1. Now suppose I have got a situation like this. I just only one vector, U1 n. Suppose I have got only one vector to, just for illustration purpose. UN has only one column vector. I will generalize it to this case, but suppose I have got only one column vector, which is U1 n. And this guy corresponds to U1 n minus 1 and then 0. Okay. There is U1 n minus 1 vector and then just have 1 0 here. You understand that pi n is orthogonal to this, because pi n has 1 in the last component, this guy has 0, and this has all zeros here, this has data. You take the inner product, even if you have lambda factor and all, it will be 0, you understand, isn't it? 1 into 0 and this data into 0. So they are orthogonal. So your pi goes this way. Pi n. Okay. Mind you, right now I am taking only this case where UN is this. So here Pn means, and Pn perpendicular, they are all related to what? The projection and projection error operator correspond to the space spanned by only one guy. Okay. You understand, na? I will be using that notation. Pn perpendicular here, but here the space is spanned by only one fellow. Just for this example, it will give you some clarity through this graphical treatment. Then I will generalize, come to the generalized case. Fine. These two are orthogonal. Now suppose I consider, but they are all length n. I consider another vector. That is your U1 n. It's a two-dimensional plane, but doesn't, from that you don't come to the conclusion that since in this figure it appears that this is lying in the plane containing pi n and these two are orthogonal, this is always expressible as a linear combination of two, because this is actually n-dimensional space. These two can be pointing in two different directions and this fellow could be pointing in another direction. I mean, this fellow may not be in the plane containing this guy and this guy, in general, not here, but in general. So don't get deceived by this fact, that I am drawing on a 2D plane. So definitely this appears to be in the same plane which contains this guy and this guy. Plane means space. Okay, in general not. Three vectors pointing in three different directions. So one is not in the plane containing the other two, or space containing the other two. Okay, in general, but here it will not be. I explained that yesterday. My claim is, if you consider U1 n and pi n, these two fellow, or to start with, if you consider pi n and this guy, and the space spanned by these two guys, or using real life geometry, the plane containing these two guys. In vector space, we call it space spanned by these two. In real life solid geometry, we call it the plane containing these two. Both will be same thing, you can always see. In that plane, any vector will be a linear combination of these two vectors. Okay. My claim is that contains this guy, first claim. That is very simple. What is U1n? U1n means this part is common. Last part, this guy gives me 0, but this guy gives me 1. So, I will take the last component of this vector U1n, the scalar element U1n, multiply pi n by that. So, 1 into U1n, that plus this guy together will give me this vector. So, this is linear. This is a linear combination of these two. Obviously, this is contained in the plane containing these two, or this is contained in the space spanned by these two. Okay. That means, if I consider these two lines, if I consider these two and consider the space spanned by these two fellows, that is a subset, or that must be contained in the space spanned by these two fellows, because this fellow is always some linear combination of these two guys. So, space spanned by these two means what? Space containing linear combinations of these two guys. Any linear combination of these two guys, you replace this by a combination of these two. So, obviously, that will be what? Finally, a linear combination of this fellow and this fellow. Isn't it? So, space spanned by pi n and U1n, that is contained in the space spanned by pi n and this guy. Okay. And reverse also is true. If you now consider this fellow, this is also a linear combination of these two guys, because U1n pi n, this I multiply by minus of the last component of this guy. So, minus of last component of this guy will multiply 1. Now, if you add the 2, last one will cancel out, you get 0 and okay, isn't it? If you consider pi n, multiply it by the minus of the last component of this vector. So, that will multiply the 1 here, and then you add the 2. So, last component and minus of that they will cancel, yield a 0 here, top one will be like this, because this is 0, so will not change anything. So, by the same logic then, space spanned by these two fellows is contained in the space spanned by these two fellows. That means, if A is contained in B and B is contained in, then A and B are same. So, space spanned by pi n and U1n and space spanned by pi n and this fellow, they are same. But here these two are orthogonal. So, if I have any third party vector, say Dn, I have to project it orthogonally on the space, because there is only one space here now, either way they are same as on that space. Then that will be what? If I view the space as the one spanned by pi n fellow and this fellow, which are orthogonal, then the projection is very easy to compute. There will be what? Projection along this component and projection along this component. Projection along this component will be what? Last guy, Dn inner product with pi n divided by norm square of pi n into pi n. Isn't it? Dn inner product with pi n will give rise to what? Last. Okay. And then norm square of pi n is 1. Pi n, norm square is 1. Lambdas will affect here. This will be free of lambda. Norm square is 1. Okay. So, last component by 1 into pi n. So, that last component multiply the 1. So, that means, can I write this way? P n, you are understanding one thing now, I am not making use of any physical geometry here. I am still using vector space logic only. My logic, I am giving a pictorial description, but my logic is purely using the axioms of vector space. So, even here if I do not draw this figure, I can write directly, because I said by linear combination approach that the one space is contained in the other and vice versa. I did not use any real life geometry for analogy and all that. Okay. So, my treatment is still purely based on vector space. So, this figure only was used to have some clarity, that is all, visual clarity you can say. Okay. So, Pn, not Pn. So, first I write span of, if I call it W pi n, span of, in this case, U1n and pi n vector, then this is equivalent to span of These two fellows that we have proved just now. This is what we proved here, isn't it? At this space I am calling W pi comma n. This space is W pi comma n. This space is W pi comma n. The corresponding projects, the total, here I consider only Wn, mind you. Here I have appended another guy pi n. There is the only difference between the two. Here it was purely use, now pi n has come in. That is why I am calling it W pi comma n. It was only purely Wn. Okay. And here the corresponding projection operators are P pi n perpendicular. Fine. You understand their meaning. Can you see I can easily write if I take the third party external vector dn, project it on this space, I use this thing because pi n and these are orthogonal. That will be what? Projection on this and projection on this. Projection on pi n will be what? dn inner product with pi n by norm square of pi n into pi n. Norm square of pi n is 1. Norm square is 1. Others are 0. This 1, 1 square 1. No lambda on that. 1. So forget about the denominator. dn vector inner product with pi n will be the last component of dn into pi n. So dn into the last component into 0, 0, 0, 0, 1. So essentially a vector where all are zeros, last one is the last component of dn, that is dn. So one vector will be zeros and then dn. There is a projection on pi n. Okay. And projection on these will be what? dn inner product with, instead of taking the inner product, let us not use that formula here, because I will be generalizing the case where not only u1 is present, so many are present. So there the inner product thing will not work. Inner product works only when there is one vector on which I am projecting. So I can say inner product between the two by norm square of that. You are projecting dn on this vector. So essentially you will be finding out a linear combiner coefficient, only one in this case. That times this vector subtracted from dn error vector, norm square of that error will be minimized. But that norm square will be what? Last component of dn okay. Last component of dn is not 0. I am doing it here, but I wanted to do it in the general case. If you permit me, because I am just not able to take the temptation of going to this general case where, I mean, we have all the vectors present. Because just, it's very silly to just deal with, that becomes very simple case actually. So up to this, I use this thing that, okay, in this figure we have found out that the two spaces are same, W pi n, you can see it this way, and any external vector can be projected using this treatment where it is simply a summation of these two projections. This we did for this case. Now I will generalize where it is not only one vector. I will generalize this statement where all the vectors are present. I will just write down these equations. And then I redo this projection for the general case, whose special case will be this, where only one column vector is present. Because that is more, that is better actually, Okay. So now, what's in this figure, I will be now generalizing. Here I had only E1 fellow. I will be considering this vector u pi n as u1n, u2n uln as before, and pi n appended. You understand this is what I did, but only one vector was present. I am just giving a name, and the corresponding space spanned by W pi n call space of u pi n, okay, and the projection operators. So you understand, I am not doing anything new, but I am just taking so many vectors at a time. I mean, I wanted to do the entire thing by one go, that not do this treatment for one vector, again redo the same thing when the general case comes. That is the reason why I chose to come to the general case directly. P pi n perpendicular, these two operators, so I don't have to write their meanings. P pi comma n is the orthogonal projection operator for this space. P pi n perpendicular is the corresponding error operator. You understand this, right? And I define the vector, say u pi prime n minus 1 as what u1 n minus 1 0, u2 n minus 1 0 dot dot dot, ul n minus 1 0 and pi n. So you understand, I am not doing anything new. Earlier I did the same with only one vector. Earlier only this u2 to ul were not present. I consider u1n appended with pi n, this, and this fellow this, and I said the space spanned by the two vectors here and here, they are same. That is what I did that time. I am not little more general. Is this essentially, earlier u2 to ul were not present. I consider u1n and pi n, and other case I consider u1 n minus 1 0 and pi n. That is what I did in this figure. Once these two, once these two. Now instead of only one vector, I am considering all of them. So here all of them having this 0 fellow. Okay. Once again, by the same logic, you can see the space spanned by this column space. You can see column space of is same as the same w pi n. I proved it here for the simple case where there are two vectors or only one u1. Same logic can be used here. Firstly, you consider this. And consider this. First, I show that column space of this column in this matrix is contained in the column space of this matrix, and then I will show the reverse. Column space of this matrix. First, consider pi n. Pi n present here, present here. Column space of this matrix means what? The space where any vector is typically a linear combination of these fellows. Pi n present, present, and any other vector if you pick up, say ukn, that is obtainable as what? A linear combination of pi n and the vector here with uk n minus 1 and 0 by that logic. By that logic, na. Suppose you consider this same thing, u1 n minus 1 0. It's very simple. u1 n minus 1 0, this vector pi n. You can combine the two to get u1 n. I have done it already. Multiply this pi n fellow with the last component of u1 n and add that with this, you get back that. Same for all the columns, and pi n also is present. So any linear combination of this fellow is ultimately a linear combination of these fellows. So that means column space here is contained here, contained in the column space here, and vice versa also. Column space of this matrix is contained in the column space of this matrix, because pi n present, and any vector here will be, say you take u1 n minus 1 and 0. That is a linear combination of u1 n and pi n. Just take the negative of the last component, multiply pi n by that, add the two. Last component will cancel out, give a 0. Very simple, just repeat, go on repeating that logic on all of them. Okay. So that means the two column spaces are same. So I am doing that now. You see, in general case, the dn is an external guy. I want to find out orthogonal projection of dn on this space. This space can be viewed as the column space of this matrix or this. But here advantage is pi n is orthogonal to each of these fellows. They are not mutually orthogonal. See, that's little difference. These fellows are not mutually orthogonal. That is the reason I wanted to be general. That when many vectors are present, they are not mutually orthogonal. That fact was not coming up there, because I just chose one fellow. So, that is why I wanted to switch over to this general case. Here, pi n is orthogonal to them. So, that means overall projection is what? Projection on the space spanned by this side plus the projection on pi n, isn't it? So, P pi n dn is what? Projection on pi n, that we have already seen what it is in the previous page. That is irrespective of whether you have one column vector or many. Projection of dn on pi n we have already seen, inner product with pi n divided by norm square of pi n into pi n, that was giving rise to 0, 0, 0 and the last component. We have seen that. Please do not ask me to repeat this. We have seen dn on pi n, we all know what it is. Now comes this bigger issue where I stopped and came to the general case. A dn to be orthogonally projected on the space spanned by this part. This matrix, this part you can even call a matrix U prime n minus 1. Pi dropped from here. U prime n minus 1 means all those vectors are there with a 0 appended. So, that means now I have to project dn orthogonally on the column space of this matrix. This pi n I have taken care of here. I have to project dn on the space spanned by these columns. That is the column space of this matrix. Please see this carefully now. Let us go to the first principle of doing orthogonal projection. How do we do? We find out a set of linear combiner coefficients by which we combine the columns, then take an error, take the difference of that combined thing from the dn fellow and take norm square of that, minimize that with respect to the coefficients, right. If you do that, just for rough work I am using this part, if you do that, you are supposed linearly combining these columns. You are linearly combining these columns. So, on one hand you have got dn fellow, and other hand you have got these columns C1 into U1 n minus 1 0 plus say C2 into U2 n minus 1 0 plus dot 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 plus say C what CL into UL n minus 1 0, isn't it? And dn, you take the error dn minus this combined thing, and that error vector norm square is to minimize with respect to C1 to CL. That is what we do. Once you obtain that optimal set, combine them, this is your projection, subtract, this is the error. That is a simple thing. Now, in that, if you find the error vector, last component will be what? Only the thing coming from here. Here all have zeros. So, the error, if you now take this, find the error and call it say En, okay. Norm square of En will be what? First take the last guy square up, no lambda there. You remember norm square, the last guy is 1, previous to that lambda square. So, last guy is d square n. Now, I will write compactly using your intelligence. Just imagine the last but one component. C1 times last component of E1 n minus 1, E2 C2 times last component of E2 n minus 1 dot 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 here. Subtract that from d n minus 1, that error square, multiplied by lambda. Previous one also multiplied by lambda square. You take lambda common. Then what you get? This isn't it simply this? You have missed out some classes, it looks like. You have missed out classes or you have not been following. What was the definition of inner product I gave? Norm square is a special case of inner product. I gave the inner product with a lambda or not, forgetting factor, so that contribution for remote past is forgotten.
So, we are using correctly definition.
I am using that definition of general definition of inner product. You are also confused about lambda, is it? Recheck your notes. So, this is, please see, d n minus 1 minus summation C I ui n minus I equal to 1 to L, this you are minimizing. ठीक से देखो, this is the thing you have to see always inside, you know. You are taking the error. Last guy, just square up. It is independent of, because of the presence of 0, last guy doesn't have any impact on the coefficients. Optimal coefficients you obtain. That is what is the crux of the story. The new data has come, but that will not change in this case the optimal combiner coefficients, because this is only square, separate term. This is when you minimize it with respect to C1, CL up to CL, this will be giving rise to nothing, 0. But what you obtain from here is what? You consider the remaining terms. You consider the remaining error terms. See, I am not writing like, you know, teaching in a school. I am not writing. You please see it yourself. The last but one term is dn minus 1. Last is dn, last but one is dn minus 1. That time C1 times E1 in n minus 1, C2 times U2 n minus 2, CL times UN minus L. That combination, that error, square multiplied with lambda. Lambda I am taking common. So that 1. Then again dn minus 2 minus C1 times E1 n minus 2, C2 times U2 n minus 2, CL times UL n minus 2, that error square multiplied by 1 lambda, because 1 lambda has taken common, so on and so forth.
So this UI should be vector UI.
This
N minus 1.
n minus 1, thank you very much indeed, yeah, thank you indeed. You should correct me, I am writing in a flow, thank you indeed, yes. UI n minus 1, n minus 1, yeah. Okay. So that means what you are doing, when you are minimizing this, you are basically minimizing this. In fact, minimizing this part, you will forget that lambda. Or when do you minimize it? When you project dn minus 1 vector orthogonally on the space spanned by u1 n minus 1 alone, u2 n minus 1 and ul n minus 1, no 0 present. What is that projection? That is the projection p subscript n minus 1 dn. Isn't it? That is, you get those combiner coefficients, you get those CIs which gives rise to, which give you this component, this thing, Pn minus 1, Dn minus 1. When you computed Pn minus 1, Dn minus 1, you get a set of coefficients by which you linearly combine un n minus 1 to ul n minus 1. Those coefficients will be come up from here. So if I now use those coefficients and combine them, last component will be 0, and above that will be this fellow only, because these vectors are combined by the same set of coefficients. Okay. Now those who are coming regularly will understand. Those who are not, who are dropping in between, they will find it difficult. Please understand. You are getting the same set of, first attack the coefficients. You are getting the same set of combiner coefficients, because minimization coming from here. It is like minimizing the norm square of what? Dn minus 1 vector and a linear combination of E1 n minus 1 to L n minus 1. That difference. That is what you do when you project Dn minus 1 orthogonal on the space spanned by E1 n minus 1 to UL n minus 1, right? So those combiner coefficients you get. Now using them, you are combining them. Last one will give rise to 0 with all zeros. But top one, when you combine, you get this. So overall thing will be what? When you are projecting Dn on the column space of this matrix, first part will be Pn minus 1, Dn minus 1, last part will be 0. This combine, these zeros will give rise to 0, combine this upper part, this will be this. That means instead of projection, I take the projection error. If I take the projection error, then from, I have to subtract this right hand side from Dn. If you subtract right hand side from Dn, this last guy goes. Last guy goes. And on top you have Dn minus 1, that minus this, that will be the corresponding error. when you subtract here, Joseph, when you subtract this right hand side now from dn, because now we are finding out the error. The last component of dn is this dn. Here also dn plus 0 dn. So, subtracted 0. The other top half is dn minus 1 vector, that minus this projection. So, it will give us the corresponding error. So, you see I am somehow able to relate this projection for the time index n minus 1 to a projection corresponding to time index n, but it is not simply Pn perpendicular dn. I have to carry the burden of this extra guy pi, whereas my intention was to have relation directly between the two. But this kind of relation does not exist, that Pn perpendicular dn is simply this. That does not exist. This is what I could do. But then how does it solve my purpose? From here, I will proceed in another way. This is what? This is again projection. This corresponds to what? Projection on the space spanned by this also. You can either view it as the projections on the space spanned by these fellows, but the two spaces are same. So, this projection, forget about the error, consider the projection. That is again projection on the space spanned by these fellows. This I can write as a direct sum decomposition of what? This component, this side, plus pi n projected you first take pi n, project it orthogonally on the space spanned by this, take the error span of that. So, at least I am able to extract out this part separately, because I finally want a Pn perpendicular dn, no pi appended. So, pi I want to take out, but I cannot throw away pi, then everything will be incorrect. Okay. So, what I will be doing here, this projection again, w pi n now you write w pi n as w n, there is a space spanned by these guys, direction of what? Span of what? P n perpendicular pi n projected on the space spanned by these fellows, that is P n pi n, and the corresponding error P n perpendicular pi n. So, in this case again, the same projection can be written as what? And then alternative by equivalent way. This projection, here I wrote like this, same projection can be written in an equivalent way here as projection of dn on wn plus projection of dn on this guy, isn't it? That means this can be written as Pn dn, okay, Pn dn plus, so at least you see Pn dn is coming and Pn minus 1, dn minus 1, they are coming. Extra terms are coming, I agree. This I cannot leave away, but at least there is some relation from n minus 1th index to nth index, isn't it? So, Pn dn plus dn on this guy. Okay, I will write the inner product later. Inner product. In the inner product, simply dn with this, but I can swap this projection operator from pi n to on dn. I am not showing that step separately, there is a sort of just space, you please understand. So, this can be written like this, pi n. When you do inner product between pi n and any other vector, you basically get the last component. So, this inner product will give rise to what? The projection error, if you take dn projected on this guy and the error, the last component of that error, isn't it? And this was only p pi n dn. So, I do the formality for the corresponding error. There is this guy, p pi n perpendicular dn was one from one approach was this, and from this approach equal to what? You subtract the right hand side from dn. So, this becomes Pn perpendicular dn, and this is minus sign only. You can write the top as the vector Pn perpendicular dn, this vector last component, nth component of that vector, divided by okay. This is a relation we will be using frequently, this one. Now, you can understand there is a direct relation between Pn perpendicular dn and Pn minus 1 perpendicular dn minus 1, but I have this additional burden. Even here also Pn perpendicular dn is coming, this guy is last component scalar, but I have these additional components. Even you will see this will not create problem when I apply it in the lattice case, this will not create problem, because I will be able to swap this Pn perpendicular from pi n to somebody else, that somebody else's last component will turn up. I will have problem with this guy. This guy will give rise to a new variable again. Like various variances we have taken, I have order updated, this will be another variable I have to live with, that means I have to update it, that can be order updated. Okay, so this is an extra variable that is generated. I mean, here I have taken Lth term, so in our case we will see we will have for every order say p vectors, so it will basically depend on order p, and this actually is basically an angle parameter. I will show you that angle parameter now, and that can be order updated. So that means lattice will not only involve forward and backward prediction errors or the respective error variances or delta. In the delta business, delta is nowhere in sight, don't get confused. Delta is inner product between two projection error vectors. Delta I have not come to, I am only updating, time updating projection error vector only, no inner product. But just hear me out, in the delta update, I will be needing this addition another variable which will come from there, and this variable then again needs to be updated, data dependent. This can be, we will see, this can be easily order updated. I will give you the meaning of this, and then we will call off for day. Pn perpendicular pi n square. If you take this to be the space W pi n, or not W pi n, just Wn, Wn, the space spanned by these guys, Wn. Suppose this is Wn, and here is your pi n, sorry, here is your pi n. So, this is your projection Pn pi n, and this is Pn perpendicular pi n. Now, you can, even without using any geometry, you all know that square of this plus square of this equal to this. That means, if I take the ratio of norm square of this guy by norm square of this guy, that will be less than 1, isn't it? Less than 1, greater than equal to 0, less than 1. So, that can always be, forget about the geometry. It is a quantity like Pn perpendicular pi n, Pn perpendicular pi n, norm square of that divided by norm square of pi n, that is can always be written as some kind of sine square theta. Since in norm square I am saying, actually if the norm instead of square, if you take the norm of this guy, Pn perpendicular pi n divided by norm of pi n, that can always be written as some kind of sine theta, isn't it? But norm of pi n is equal to what? 1. This guy's norm is 1. Last component is 1, others are zeros. So that means norm square of this guy can always be equated with some kind of sine square theta. In this geometry, geometrica, this, where I am drawing the analogy, you can take that this to be that angle. That is why this quantity is called the angle parameter, which is to be updated. I still took the general case of U1L, U1N up to ULN. I have not used this in the specific case of lattice. I gave you so far the general result, but my starting point was updating delta Pn. These results can be very quickly and very nicely used now in updating delta Pn. I suggest that when you come for the next class, please come prepared with this. Please, I will not rewrite these relations. I just cannot, because I am running short of time. I will not. Every class I say this, but I do recap. This cannot be done. I simply, please on Monday you come with this. I will wind up this topic in 10-15 minutes time, which I could not do today. And then I want to move to another topic, another version of RLS filters, which is also very good, which leads to a systolic array actually. Okay, that's all for today. Thank you very much.